So before we move forward with using our higher order quadrature, it's important to consider some of the potential pitfalls in terms of error terms that could impact the quality of your quadrature. The three main ones are aliasing, truncation, and an inexact quadrature. Aliasing is perhaps a similar concept to most viewers. This occurs when the function itself has a much higher frequency than the interpolation that we're attempting to use. So you can imagine here's a relatively high frequency function. If we're choosing interpolation points at not frequently enough to capture all the extrema, then we may get some sort of lower order harmonic of the function itself. So we could get something that maybe looks like this. Generally, it's not too much of a problem because typically the solution approximation is chosen to be either sufficiently granular so that the analytical function that you're integrating is not changing quickly enough, or that you're using a high enough order quadrature to capture the frequency. The second piece is unavoidable in the sense that if the exact function isn't exactly representable in the order polynomial space that we're using for the quadrature, then you're inevitably going to have to truncate some portion of terms, especially if it's an infinite series. The third possible source of error is inexact quadrature. This results when the total polynomial order of the product of the interpolated functions that you're attempting to perform quadrature on exceeds the exactness of the quadrature. So for the Gauss-Legendre quadrature, this isn't much of a problem typically for one or even two functions. We can think of this because for a particular quadrature, for Gauss-Legendre, it's 2m minus 1 order accurate. But if we think of two functions that we'd like to integrate, each interpolating at those m points, these two functions are m minus 1 order accurate, so that the total order of the polynomial that you're attempting to interpolate is 2m minus 2. So 2m minus 2 is less than 2m minus 1, so therefore the quadrature is exact. It could be a problem if you're attempting to look at the quadrature of the product of three functions, or if you're using something like a Gauss-Leibniz quadrature, which is 2m minus 3 accurate, which would not be exact for the product of two interpolations.